Hello and welcome back. A few videos ago, we introduced the concept of the electric field. And basically, the electric field described the tendency for the environment to exert a force on a charged particle if it were added to the system. And because the force that is exerted on a charged particle depends on the charge of that particle, we defined the electric field as being equal to the force that would be exerted on a charged particle if it were added to the system, divided by the charge of that particle. And so this quantity now only depended on the environment of the system. In a similar way, I want to introduce the concept of the potential. So what the potential will do is the potential describes the change in the potential energy that would occur if we add a charge to the system. So we define the potential as being equal to the change in the potential energy that occurs when we add a charge to the system, divided by the charge of this particle. So once again, we have a quantity that only depends on the environment of the system. Now, like always, whenever I introduce a new concept like this, I like to step back and apply dimensional analysis and look at the units of this quantity. So we defined the potential as being equal to the change in the potential energy that occurs when we add a charge to the system, divided by the charge of this particle that we've added. So this is going to be equal to, potential energy has units of joules, so I'm looking at the units of these quantities here, and we're going to divide it by charge, which has units of coulombs. So we can see that the potential has units of joules per coulombs, and we call this quantity a volt, which we just denote with a V. So this is why you'll frequently hear people refer to potential as voltage, and it's really the only quantity I can think of where we do something like that, where we name the quantity in terms of its unit. You don't hear people refer to mass as grammage or something like that. But potential is very frequently referred to as voltage. I think so it doesn't get confused with potential energy. So since we now have a definition for the potential, let's go ahead and look at a couple of formulas which we can use to calculate the potential of a system. So let me go ahead and open up a blank screen here, and let's consider a simple example where I have a charged particle here. And I want to calculate the potential associated with this particle. Well, we said the potential is equal to the change in the potential energy that occurs when I add a particle to the system, divided by the charge of this particle that I'm going to add. So let me call this Q1, and let's consider how the potential energy changes if I add another particle. We'll call this Q2. So the potential energy is going to increase, and the potential energy is going to become K, Q1, Q2, divided by the distance between the particles. And I'm supposed to divide this by the charge of the particle that I've added. In this case, that's going to be Q2. So we see the Q2 cancels, and so we see that the voltage that is associated with just a single charged particle, so this is just this particle by itself, has a voltage that's given by this formula here. It's going to be equal to K, Q, divided by the distance from this particle. And again, just like the electric field, there is a voltage or a potential associated with every single point in space, and that would describe how the energy would change if I added a particle to that point in space. So we can see that the voltage increases the closer we are to this particle, because if I add a particle right here, the energy is going to increase more than if I add a particle that's really far away. Another thing we talked about in the previous video was how to calculate the potential energy of a large system of particles. So what if I had, let's say, another charge, we'll call this Q3 here, and Q2 over here. And let's consider what happens if I add another charge right here. So the idea is that the voltage is equal to the change in the potential energy that occurs when I add a charge to the system, divided by the charge that I add. So I'm going to add a charge Q4 to the system. Now, I want to point out that even before I add this charge, this is already a pretty complicated thing. Remember that when you have multiple charges, the total potential energy is the potential energy associated with each pair of charges. So there's already a potential energy associated with this pair, and this pair. So if I add another charge, the point is that the potential energy associated with this pair and this pair and this pair. That hasn't changed. That was there before, and now that I've added that particle, that potential energy is still there. The only change in the potential energy occurs due to the interaction between particle 1 and 4, particles 2 and 4, and particles 3 and 4. So we would say that the potential is now going to be equal to K times, let's see, it's going to be Q1 divided by, I'll call this R1. R1's the distance between particle 1 and particle 4, plus K Q2 divided by R2, plus K Q3 divided by R3. Right? Because the potential energy associated with this would be K Q1 Q4 divided by R1. R1's the distance between these particles, but then I divide by Q4. So this is what I get for the potential associated with these two particles. And then the potential is also going to increase because of the interactions of these two particles and these two particles. So we see that the total potential associated with these three particles at this point right here is given by this formula down here. Oops, so I just closed that, but one of the important things to understand about the potential is that calculating the potential for a large group of particles is much easier than calculating the total potential energy of a group of particles. And the reason is that each individual particle only contributes one term to the total potential. However, if you have a large group of particles, the total potential energy is much more complicated because you have to worry about every pair of particles. So there's that whole combinatorics type of thing that makes it much more complicated to calculate the potential energy than to calculate the potential. Now there was one other formula we had for calculating the difference in the potential energy between 2 points. So if I have a charged particle Q placed in an electric field, and I want to calculate the difference in the potential energy between the particle being at this point, and if the particle moves some distance s to this point, we said that the difference in the potential energy between these 2 points is equal to the charge of the particle times the component of the electric field that's parallel to the displacement times the displacement. And actually I need a little negative sign there. And because the voltage is defined as the difference in the potential energy that occurs when I add a particle divided by the charge of this particle, we see that the difference in the voltage between 2 points in space is equal to minus the component of the electric field that is parallel to the displacement between those 2 points divided by the displacement between the 2 points in space. So this describes basically the difference between how the energy would change if I add a particle here and how the energy would change if I add a particle to some different point in space. And the reason this negative sign is here is because the potential energy decreases as the particle moves in this direction, right? So if we think about a positive charge in the electric field, there's an electrostatic force that's going to push this particle to the right. So what's happening is that this particle is speeding up because there's a force pushing on it to the right. So we say that the electrostatic potential energy is being converted into kinetic energy as this particle moves towards the right. So down here we have less potential energy than up here. And when we move in this direction, the electric field and displacement point in the same direction. So that's why there's this negative sign in the voltage and in the potential energy. I think I may have left out that negative sign when I talked about potential energy earlier. So at this point, we've introduced 4 different quantities. We've talked about the force that is exerted between charged particles. We've also talked about the potential energy associated with a group of charged particles. And we've talked about the electric field and the potential. And at this point, I want to just step back and look at the relationship between these 4 quantities. So we have some quantities that describe the force that is exerted between charged particles. So for example, we have Coulomb's law, which says the force between 2 charged particles is given by K, Q1, Q2, divided by the distance between the particles. We can also write the force in terms of the electric field using this formula. And so this quantity describes the forces that are actually exerted on a particle. We also have quantities that describe the force in terms of the environment. So, for example, we have the electric field, and the electric field describes the tendency for a system of particles to exert a force on a particle if it were added to the system. And the way we go between force and the electric field is we calculate the force that would be exerted on a charged particle, and then we divide this by the charge of the particle that we're adding. So all we do is we take these formulas up here and we divide by the charge. So for example, the electric field that is caused by a single particle is equal to, so we take this formula here and we divide by Q. So it's just KQ divided by R squared. So we can easily see that the way we go between looking at an actual force and the electric field, which describes the tendency for an environment to exert a force on a particle, is that we just divide by Q. So we take this formula up here and we divide by Q. So this is something that describes the environment. Now we also have some quantities which describe the potential energy. So for example, the potential energy of two charged particles is given by this formula here. So it's equal to K Q1 Q2 divided by the distance between those particles. Also, we could describe the difference in the potential energy between 2 points in terms of the electric field, and that's equal to K times the component of the electric field that's parallel to the displacement times the displacement. And one thing that I want to point out about this is that when we go from forces to potential energy, we always multiply by a distance. So for example, in going from this formula to this formula, we multiplied by r, which was the distance between the two charged particles. And when we go from this formula to this formula, we multiply by the displacement between the two places. Finally, we also have a quantity which describes how the potential energy of a system changes when we add a particle. And again, this is something that describes energy, but it's also describing the environment. So it's describing how that environment behaves. So how the potential energy of the system will change if I add a point particle. And we describe this using the potential, or the voltage. And again, it's the same idea. To go from this to something that's describing the environment, I calculate how the potential energy would change, so the change in the potential energy, and then I divide that by Q. So again, we're taking these formulas up here, and we're just dividing by Q. So I can see that the voltage that is created by a single point particle is just equal to KQ divided by R. So I've taken this formula up here, KQQ divided by R, and I just divided off one of these Q's, and that's how I get the potential. So this is a really useful thing if you can step back and see the relationship between these four quantities, because if you understand how all of these quantities are related to each other, you can really just sit down and remember two formulas. You know, the force that is exerted between 2 point particles, and how the force can be described in terms of the electric field. And if you know these two quantities, and you know how all of these other quantities are related, then you can say, well, I have the force formula. If I want the potential energy, I just multiply by the distance between the particles, and I get this formula here. Or if I want the electric field, I just divide by a charge. Or if I want the potential, I calculate the potential energy, and then I divide by charge. So it really makes things a lot easier if you understand how all four of these quantities are related to each other, because you can basically, instead of remembering, however many equations I have here, I think I have like 7 equations, you can instead just remember 2. Now, one last thing I want to look at before we go ahead and start looking at examples is how the potential is related to the force that is exerted on a charged particle. And so in this example here, I show a positively charged particle that's placed between the plates of a capacitor. And we have these electric fields that are going from the positive charges to the negative charges. And remember that the electrostatic force is equal to the charge times the electric field. And because this is a positive charge, that means this force is going to point in the same direction as the electric field. Another way to think of this is that the positively charged particle will be repelled from this positively charged plate and be attracted to the negatively charged plate. So the force that's exerted on this particle is going to point towards the right. So if we think about this, remember the voltage, or the potential, is given by this formula here. So KQ divided by the distance. And Obviously, this is a little bit more complicated than a point charge, but this is a positively charged plate. That means that the voltage at a point like right here, right outside of this, is going to be a positive voltage. So right outside of a positively charged plate, the voltage is positive. Over here, we have a negative charge, so we're going to have a negative number up here when we calculate the voltage. So at a point over here, our voltage is going to be negative. So we can immediately see that a positively charged particle moves from a place with a high voltage towards a point where the voltage is lower. And what this means when we talk about circuits a little bit later on in the year, what this means is that the current always flows from a high voltage towards a low voltage. That is, that positively charged particles will always move from positive voltage to negative voltages. So let's go ahead and look at a couple of examples. The first example says, an electric car runs off of a 290 volt battery. 1200 coulombs of charge pass through the car's battery when the car accelerates for 7 seconds. The question asks us to determine how much power was produced by the battery during this time. So remember that power describes the change in energy, or really I should say it's the work that's done per unit time. And in this case, we can say that this is going to be related to the change in the potential energy of these electrons divided by delta T, because the only work that's being done is the work that's done by the electrostatic force on the charge in the battery. So we have that the power is going to be equal to the change in the potential energy of the electrons, or whatever it is in the battery, divided by delta T. So I know delta T, I'm trying to solve for the power, and I need to find a way to calculate the change in the potential energy. Well, I'm told the charge is 1200 coulombs, and the 1200 coulombs is going to go through a voltage difference of 290 volts. So the change in the potential energy is going to be equal to Q times delta V. Remember, that's the relationship between potential energy and voltage. Right? We have that the voltage is equal to the change in the potential energy divided by charge. So the change in the potential energy is just Q times V. So now if I solve for the, well actually I've already solved for the power, if I just plug all this into a calculator, I'm going to see that this power is going to be equal to 39.7 kilowatts. So that's how much power was produced by the car's engine. Of course, that doesn't necessarily mean that all of that will be converted into power that the car can use, but that's how much was lost, the rate that energy was being lost in the battery. So let's go ahead and look at another example. This is a very similar example. It asks, how many electrons move through a 60-watt light bulb in 1 hour when it's connected to a 12-volt battery? So again, we can say that the power, remember, is equal to work divided by delta T, and here the work is being done on the charge that's moving through the light bulb. And that's going to be equal to the change in the potential energy of that charge. So this is equal to the change and the electrostatic potential energy of the charges divided by delta T. And the change in the potential energy, remember, is just going to be equal to Q times the voltage difference that the charge moves through divided by delta T. And in this case, it's asking me how many electrons move through the battery. So what I'm really solving for is the charge that moves through the battery. So let me go ahead and write this down. So I have power is equal to the charge that moves through the light bulb divided by the voltage difference across the light bulb, and all of this divided by delta T, because I'm looking for the power, not just the energy. So again, I want to solve for the charge. So the charge is going to be equal to, so I'm going to multiply delta T over here, so I have power times delta T, and then I'm going to divide by the difference in the voltage across the battery. So if I plug this into a calculator now, this will tell me the total charge that's going to move through the light bulb. But what I want to know is how many electrons move through the light bulb. Remember that every electron has a charge of minus 1.6 times 10 to the minus 19 coulombs. So if I know the total charge that passes through this, then the total number of electrons is just going to equal that charge divided by the charge of an electron. So I take this formula here, power times delta T, and then I'm going to divide this by the electron charge times the difference in voltage. And if I plug this into a calculator, I'll see that it's going to be equal to 1.13 times 10 to the 23rd electrons. And of course, remember that if my power is measured in watts, which it was, then delta T has to be measured in seconds. So this is 3,600 seconds. That's how many seconds are in 1 hour. So let's go ahead and look at one last example. This example says we're given these 2-point charges, a plus 2q charge and a minus q charge, that are separated by a distance d. And we're asked to find the 2 points along this line connecting these two charges where the voltage is going to be equal to 0. So the first thing I want to point out is that the voltage can actually equal 0 at certain places, because the voltage is equal to kq divided by the distance between the 2 points. And because the voltage depends on the charge, voltage can be either positive or negative. So the voltage right outside this negative charge is negative, the voltage just outside this positive charge is positive, so somewhere in between those two voltages are going to cancel out. And there's actually 2 places where the voltage is going to equal 0. The first thing I want to look at is this point in between them. So let's look at a point, let's say right here. And let me call the distance between the negatively charged particle and this point x. This is what I'm solving for. So I'm going to try to figure out how far from the negatively charged particle this point is where the voltage is equal to 0. Now, if these two charges are separated by a distance d, and this distance here is x, then the distance between the positive charge and this point is equal to d minus x. So now I can plug these two things into the formula for the potential. Remember that when you have multiple charges, the total potential is equal to the potential due to this charge plus the potential due to this charge. So my total potential is going to be equal to, potential is V. This is going to be equal to, we'll have K times 2Q divided by the distance D minus X plus K times minus Q divided by this distance, which is X. So I want to solve for when that's 0. So let me go ahead and write that down again. So I have K 2Q divided by the distance D minus X, and then I had minus Q divided by X. I have a K here as well. Notice that Q and K appear in both of these, so I can factor that out. So I can say that this is going to be equal to KQ times 2 divided by D minus X minus 1 over X. And I'm trying to figure out when this is equal to 0. And since I'm setting this equal to 0, I can just divide off these two numbers, because K and Q aren't going to equal 0. And so I'm going to see that I'm solving for when 2 divided by D minus X minus 1 over X, D minus X, divided by 1 over X, I'm trying to solve for when this is equal to 0. So I could rewrite this as 2 divided by D minus X is equal to 1 over X. Then I'm going to go ahead and multiply both sides by X times D minus X. If I do that, I'm going to get 2X is going to be equal to D minus X. If I add the X over here, I'm going to have 3X is equal to D. So I see, I'm running out of room here, but X is going to be equal to D divided by 3. So this is my first solution here. So in between, if X is equal to D divided by 3, then the voltage is going to be 0. So that means that this distance here is twice as much as this distance here. So this is D thirds, and over here we have 2/3 of D. And again, that kind of makes sense, right? This is twice the charge, so the distance has to be twice as much. This is half the charge, so the distance over here is half as much as this length. Now it turns out that there is one other place where the voltage is going to be equal to 0. And let's just step back and think about where this other point is going to occur. So remember that the voltage decreases with the distance. It goes KQ over R. And it's proportional to the charge. So if I look at the voltage, let's say right outside of this positive charge, the magnitude of this voltage is larger than the magnitude of the voltage just outside of the negative charge, because this is a larger charge. However, as I move away from this positive charge, the voltage due to this positive charge decreases. So the idea is that if I go out somewhere over here, the negative charge due to this charge here, the negative voltage due to this negative charge right here is going to be somewhat large because I'm close to the negative charge, And the positive voltage, due to this positive charge here, is going to be decreased because I'm further away from that positive charge. Okay? So I'm going to try to find a point over here to the right. So I'm decreasing the voltage due to the positive charge because I'm far away from it, and hopefully that's going to make up for the fact that this charge is smaller. So if I consider a point over here, I'm going to call this again x, or actually I should say the distance between the negative charge and this point is going to be x. If the total distance between these 2 points is d, then the distance between the positive charge and this point over here is equal to d plus x. So the potential at this point over here is going to equal k times 2q divided by the distance between this charge and this point, which is d plus x, plus k times this charge, which is minus q, divided by the distance between this charge and this point over here, which is just x. So again, I want to solve for when this is equal to 0, so we have k, 2q divided by d plus x, plus k times minus q divided by x. I'm going to set this equal to 0. Again, I can factor out the k and q because it appears in both terms, so this is equal to kq times 2 divided by d plus x minus 1 over x. And so I can divide off the k and q again. If I do that, I have that 2 divided by d plus x minus 1 over x needs to be equal to 0. Again, I'm going to multiply both sides by x times d plus x. If I do that, over here I'm going to have 2x, and on this side I'm going to have d plus x. So if I look at this, I have, actually I'm sorry, it's minus the quantity d plus x. So I'm going to have x minus d is equal to 0, so x is equal to d. So this is the other place where the voltage is going to be equal to 0. So if I'm a distance d to the right of this particle, then the distance between this point and this particle is 2d. The distance between this particle and this point is 1d, and the voltages between these two things is going to cancel out. So hopefully that makes sense, that because this charge is twice as much, if I go twice as far away, then the voltages between this particle and this point and this particle and this point will cancel out. So at this point, I think I'm going to end this video, and in the next video, I'm going to talk about something called equipotential lines, which is a useful way for visualizing how the potential changes when you move from one point to another.